Okay, today we'll be talking about the EMF induced by changing the area. An elastic metal loop which is stretched to a radius of 14 cm is placed in a uniform magnetic field. The magnetic flux density of 0.75 Tesla passes perpendicularly through the plane of the loop. The loop suddenly shrinks to a radius of 9 cm in 0.16 seconds. Determine the induced EMF in the loop and state the direction of the induced current. Okay, so you use this equation because you know that the Faraday's law states that the EMF induced is directly proportional to the rate of change of magnetic flux linkage. So you know that E equal to negative dN phi over dt. And then I know that because there's only one loop, so n equal to 1. So I didn't state n here. Okay, and then phi equal to b dot a. And then you know that b is into the page, and then the area vector is also into the page. So because b and a are parallel, then you get rid of the dot product. Okay, so you use a partial derivative. And then you know that actually the magnetic flux density B is a constant. When B is a constant, dB equal to 0. So this term equal to 0. Okay, so dA over dt is final area minus initial area divided by time taken. Okay, so you can get the back EMF, which is the induced EMF. And then you know that when the area is becoming smaller, the magnetic flux linkage of the elastic metal loop decreases. So Lenz's law states that the induced current will flow in a direction such that the magnetic field produced by the induced current will always oppose the changing magnetic flux that produces the induced current. So you know that the induced magnetic field will also be into the page. Therefore, by using right-hand grip rule, you know that the current must be in the clockwise direction. But then actually, in reality, it's quite difficult to adjust the area of the metal loop. Okay, so instead of dealing with this kind of situation, normally we deal with this kind of situation. Okay, so now we talk about the induced EMF in a linear conductor of length capital L. Okay, so this is the conducting rod, and then the conducting rod has a length of capital L. Okay, so these are metal tracks. Okay, and then in this case, we assume that the metal tracks are perfectly smooth. That is, we neglect the frictional force. So the distance between the parallel metal tracks is the small l. And then you know that there's a hand pulling the conducting rod. Okay, so that the conducting rod is moving at a velocity v. Okay, so this is your ammeter, this is your resistor. And then this forms a closed circuit. Okay, so you still remember your Fleming left-hand rule? Fleming left-hand rule says that if your thumb and your first finger and your second finger are right angles to one another, and then this is F, this is B, this is V. Okay, this is the magnetic force on the free electrons, this is the magnetic field, and then this is the velocity of the free electrons. So for example, in this case here, we know that B is into the page and then V is here. So we know that the magnetic force on the electrons is here because the electrons are negatively charged. So when the electrons are moving downward, we know that the motion of the free electrons must be opposite to the direction of the current. So when the electrons are moving downward, therefore the current must move upward. Okay, so this is the direction of the induced current. And then actually you can also use the Fleming right-hand rule, where this is the motion, this is the magnetic field, and then this is the direction of the induced current. So by using, in this case here, motion is to right and then magnetic field is into the page. So you know that the induced current is in upward direction. And then when there's a current in the conducting rod, you know that there must be a magnetic force acting on the conducting rod as a whole. Okay, so FBI. Okay, so you know that the magnetic force on the conducting rod is to left. Okay, which is this. The magnetic force on the conducting rod is to left. Okay, just now I say that the magnetic force on the free electrons is in downward direction. But then the magnetic force on the conducting rod as a whole, okay, is to left. Okay, and then actually, do you know why I put this chapter inside the EMF induced by changing area? Okay, because actually this is an enclosed area. So for example, when the conducting rod is here and then it moves to here, this is the original area. This is the final area. Okay, so you know that there is really a change in the area of the conducting loop. But this time our loop is rectangular shape. Okay, just now our loop is circular shape. Okay, just now the loop is circular, but then now the loop is rectangular. Okay, so let's derive the induced EMF. Induced EMF equal to dNV over dt, and then we know that there is only one loop, so n equal to 1. Okay, so you know that actually you should always remember there's always an n here. But then in this case, n equal to 1 because we only have one loop, so of course you don't have to write n anymore. And then phi equal to b dot a. Okay, b is into the page, and then the area vector is also into the page. So you know that B is parallel to the area vector. So when they are parallel, then you can get rid of the dot product. And then you do your partial derivative. Okay, and then you know that the magnetic flux density is a constant. So B is a constant. dB equal to 0. And then what is dA? Okay, just now I said that this is the original area. And then this is the final area. Okay. Let's say that if the conducting rod move from here to here, okay? So the area swept through by the conducting rod is actually this one, you know. Okay? So the area swept through by the conducting rod in the complete loop is L times X, where X is the displacement moved by the conducting rod. X is here to here, and then L is the length between the metal tracks. Okay, this is very important because I purposely say that the length of the whole conductor is capital L, and then I say that the length between the metal tracks is small l, because I want you to realize that we use the small l instead of the capital L, because this is the area change of the loop. Okay, so you don't consider this, you only consider this. Okay, and then actually from the perspective of microscopic, you can think the situation is like this. For example, just now I said that the magnetic force on the free electrons is in downward direction. If the free electrons here move to here, then the free electrons are now inside the complete circuit. But then if the free electrons are here, then they will be deflected downwards. Okay, so the electrons from here onwards will be deflected at this end of the conducting rod. So the free electrons can never travel in a complete circuit. That's why when I derive the back EMF, I only consider the length here, okay? Because for the length here and for the length here, they do not contribute to the back EMF, okay? So please notice that I use small l instead of the capital L. Okay, so what is dl over dt? The length between metal tracks is a constant, so dl equal to 0. dx dt, okay? X is the displacement. Let's say here is x1, here is x2. Then dx equal to x2 minus s1. So actually dx dt equal to velocity, equal to the moving velocity of the moving conducting rod. Okay, so you can say that induced EMF equal to BLV, and then you realize that this induced EMF comes from the velocity. That means that it comes from the motion of the conducting rod. Therefore, we call this as motional EMF also. So next time when you hear about motional EMF, it's exactly this one. Okay, I just use another name to say this. Okay, so induced current equal to the induced EMF divided by the resistance in the loop. We assume that we don't have any resistance here, and then we don't have any resistance here. We don't have any resistance here. That's why I use R for this resistor only. Okay, and then this is the induced current. So you know that the induced current is in this direction, and then you know that when the conducting rod is moving from here to here, the whole area of the loop becomes larger and larger, and therefore the magnetic flux linkage of this loop increases. So according to Lenz's law, the direction of the induced magnetic field must be out of the page, okay, to oppose the increasing magnetic flux linkage with the whole loop. And then you use a right-hand grid rule. This is the direction of the induced current, right? Okay, so the induced magnetic field is out of the page. Okay, so this once again confirm the direction of the induced current. Okay, but then just now I already tell you how I get this direction of induced current, right? That means that you use a familiar hand rule, and then you find out that the magnetic force on the free electrons is downward. Therefore, you know that the induced current is in upward direction. Okay, but then you can also consider it from the perspective of the magnetic flux linkage of the whole loop to find out the direction of the induced current also. Okay, for example, if now the conducting rod is moving to here, okay, from here to here, you know that the area decreases. Okay, so you know that the direction of the induced magnetic field must also be into the page. Okay, so when you want your induced magnetic field to be into the page, then of course your current have to be in this direction. Okay, because when you use here, you know that the magnetic field is into the page. Okay, so you know that the induced magnetic field is into the page. So you know that the direction, when the direction of the moving conducting rod is opposite, then the direction of the induced current is also in opposite direction. Okay, so make sure you know how to get the direction of the induced current. Okay, so when there's current moving here, you know that there's magnetic force acting on the moving conductor, okay? Because BIL, you know that there's B, there's I, and then there's L, okay? So of course there's some magnetic force acting on the conductor. And then this magnetic force, which is this green color one, okay, is BIL. And then you notice that once again I use small l, okay, which is the length between the metal tracks, because the current can only flow from here to here to here to here to here. Okay, so actually there's really no current here, and there's really no current here. So when there's no current moving in this section and there's no current moving in this section, you know that you don't have to consider this and this length anymore. Okay, so that's why I use small l instead of capital L. Okay, so this is the magnetic force acting on the conductor rod as a whole. Okay, BIL, and then the I is induced current. Okay, and then induced current equal to induced EMF over the resistance. Okay, and then the electrical power is I square R. Okay, the electrical power is the heat dissipated per second by the resistor. Okay, so you know that the electrical power is of this expression. Okay, so now if V is a constant, that means that if the moving rod is moving at a constant velocity, then there is no acceleration of the conductor. When there's no acceleration, F equal to ma, F equal to m times 0. So you know that F equal to 0. So you know that the net resultant force is 0. So when the net resultant force is 0, you know that the magnetic force and mechanical force are of the same magnitude but of opposite direction. Okay, so the mechanical force is equal to the magnetic force, and then magnetic force is of this expression, okay, where we have derived just now. Okay, so the mechanical power on the conductor, which is the work done onto the conductor by the mechanical force per second, is F times V. Okay, so is this expression, and then you know that actually this expression is exactly the expression of the electrical power. So you know that when V is constant, the mechanical power is equal to the electrical power. So you know that the work done by the mechanical force is equal to the heat dissipated by the resistor, okay? Because electrical power is the heat dissipated here. But then all of these are only valid when V is a constant. For example, if you pull your conducting rod such that the velocity increases, okay, so you know that the conducting rod really experiences an acceleration, okay, because it moves from very slow and then to very fast. So when V is increasing, you know that the acceleration is greater than 0. So when the acceleration is greater than 0, you know that there must be some net resultant force on the conductor. Okay, so you know that your mechanical force is greater than the magnetic force. Okay, so when your mechanical force is greater than the magnetic force, we don't know the expression for the mechanical force. Okay, that means that because the mechanical force is provided by your hand. Okay, so if the mechanical force is greater than the magnetic force, we cannot find any expression for mechanical force, and therefore we don't know the expression for the mechanical power, okay, unless further information are given. Okay, so when V is increasing, you know that the mechanical power is equal to the electrical power plus the increase in the kinetic energy of the moving conducting rod per time. Okay, so this is the energy conservation when V is increasing. Okay, just now when V is constant, you know that the mechanical power equal to electrical power because there is now no more increase in kinetic energy. But then if now the V is increasing, you know that there must be some increase in the kinetic energy. So if you don't want to use power, then you also can use work done, okay, because you know that power equal to work done divided by time, okay, because the power equal to energy divided by time. Okay, so you know that the work done by the mechanical force is equal to the electrical energy dissipated as heat by the resistor and the increase in kinetic energy of the moving rod. Okay, so in this case, we already neglect the frictional force. If there's really frictional force, then I would say that the work done by the mechanical force is equal to the electrical energy dissipated as heat by the resistor plus the increase in kinetic energy of the rod plus the work done against frictional force. Okay, so this is the principle of conservation of energy. So of course, if your V is a constant, or if you want your V is increasing, then of course you have to supply your mechanical force forever. Okay, that means that if you want the conducting rod to be moving with a certain velocity forever, then you have to give your mechanical force forever. And then you always remember that the mechanical force is the same direction as the V, because you pull the conducting rod by your hand, okay? And then you always remember that the magnetic force must be opposite to the mechanical force forever, okay? So, for example, a conducting bar of mass m and length L moves on two frictional parallel rails in the presence of a uniform magnetic field directed into the page. The bar is given an initial velocity vi to the right and is released at time t equal to 0. Find the velocity of the bar is a function of time. Okay, so you know that when you give the conducting bar a certain velocity, then you don't provide your mechanical force anymore. So you know that the velocity must decrease. That means that the rod cannot simply move forever. Okay, so you use this expression. The magnetic force equal to negative ma. You use negative sign here because the force is opposite to the motion of the conducting rod. Because you know that the force will decelerate your moving conducting bar. Okay, so BIL equal to negative MA, where A equal to dV over dt. Okay, and then I is the induced current. Induced current equal to the induced EMF divided by R. Okay, so you know that when you see dV and then you see dt, you know that you have to use a powerful integration. Then only you can give me this expression. The final velocity equal to initial velocity times the negative exponential function. So when time is infinity, that means that when the time is very large, you know that Vf equal to VIE negative infinity. So Vf equal to 0. Okay, so eventually the rod will comes to a stop. Okay, so alternatively, you can also use your energy approach. Okay, loss in kinetic energy of the moving rod is equal to the heat dissipated by the resistor. Okay, so you can also get the same expression. Okay, so the rest of the answer is still the same. Okay, you just copy paste here, okay, to here. Okay, so actually this is not in your STBN syllabus, you know, because this is, I think this is far too difficult for you. But then I want to tell you that you don't expect that the bar can move with a constant velocity forever unless you use your hand to provide the mechanical force forever. Okay? So a linear conductor is moving on a pair of metal tracks with a constant velocity of 2 meters per second in a uniform magnetic field of 0.75 Tesla directed into the page. Please calculate the induced EMF and induced current in the conductor. Okay, so you know that E equal to BLV. Okay, therefore you can get the value for the induced EMF, and then E equal to IR. Induced EMF equal to the induced current times the resistance. Okay, so you can get the magnitude of the induced current. And then in order to find out the direction of the induced current, first you can use a Fleming left-hand rule, FBV. And then because the electrons have negative charge, so you know that the magnetic force on the electrons, on the free electrons, is in downward direction. So when the free electrons want to move in downward direction, the current is in upward direction, because you know that the direction of current is opposite to the direction of the motion of the free electrons. Okay, so the current is like this. Okay, but then if you consider this whole loop, when the rod is moving from here to here, originally the original area is like this, but then ultimately the final area is like this. So you know that the area of the conducting loop increases. So you know that the magnetic flux linkage with the loop increases. So according to Lenz's law, the direction of the induced magnetic field must be out of the page. Okay, so this is the direction of the induced magnetic field. And then in order to produce the induced magnetic field to be out of the page, then of course the current should be in this direction, because by using your right hand grip rule, okay, you know that the direction of the induced magnetic field by the induced current is out of the page. Okay, so you already know how to get the direction of the induced current. Calculate the magnetic force acting on the conductor, F equal to BIL. Okay, so once again you remember that I use L, small l, where the L is the length between the metal tracks. But then actually you only care about the L when you are given two different lengths. Normally in the examination you are only given a certain length. Okay, so normally you don't have to care about the length a lot. Okay, because normally this length and this length are very small, so normally we can neglect the effect at the edge of the conducting rod. Okay, so find the direction of the magnetic force acting on the conductor. You know that FBI, okay, when the current is in here, and then when the magnetic field is into the page, then the magnetic force on the conducting rod is to left. Okay, determine the magnitude and direction of the mechanical force on the conductor. When you see the word constant velocity, right? What do you understand by constant velocity? When it is constant velocity, the acceleration is equal to 0, so the net force is 0. So you know that mechanical force is equal to magnetic force. Okay, so the mechanical force is equal to magnetic force, which is 0.8 Newton. And then you know that because the motion is to right, of course your direction of mechanical force is to right. And then once again, you really have to remember that the magnetic force acting on the conducting rod is always opposite to the direction of the mechanical force acting on the conducting rod. Okay, there is really no way that they will be in the same direction. Okay, they will always be opposite. State the energy transformation. Okay, so you know that since the rod is moving at constant velocity, so you know that there must be no gain in the kinetic energy of the rod. So all the work done by the mechanical force is transformed into the heat energy dissipated by the resistance. Okay. A conducting rod being pulled from rest, that means that the initial velocity is 0. To move with a constant acceleration means the velocity is increasing constantly in a uniform magnetic field on two horizontal tracks of negligible resistance. The tracks are connected to a resistor R at both of its ends, which graph shows the variation of the induced current with time t for the conducting rod. Okay, the induced EMF equal to BLV, and then V is the velocity of the conducting rod. Velocity equal to displacement over time. Okay, and then the back EMF divided by the resistance is equal to the induced current. So you know the induced current is inversely proportional to time. So this is the correct answer. Okay. A conductor of length L moving down an inclined plane formed by a pair of smooth conducting rails is shown. A uniform magnetic field B is applied vertically downwards. Write an expression for the induced EMF between the conducting rails when the conductor has traveled a certain distance s along the inclined plane. Okay, so the distance is along the inclined plane. Okay, first of all, you know that you have to find a component of magnetic field perpendicular to your motion. Okay, because when you are using the E equal to BLV, you really have to make sure that the magnetic field is perpendicular to the velocity of the moving conductor. Okay. Just now, when you use E equal to BLV, when the motion of the conducting rod is here, the B is into the pitch. So you know that B is perpendicular to the motion of your conducting rod. So by the same reasoning, you have to make sure that you can find out the component of the magnetic field, okay, the magnetic flux density perpendicular to your motion. That means that when the magnetic flux density is acting downward, you have to resolve it to this direction, okay, where the direction is perpendicular to the motion of the conducting rod, okay. So you have to find out this magnetic component, okay, which is B cos theta. And then you know that you are not given V in the question, so you have to express V in terms of the variables given by the question or in some constant, okay. So for example, if you consider the slanting motion, which is the motion along the inclined plane, V squared equal to U squared plus 2s. U is the initial velocity. You know that the conductor starts from rest, so the initial velocity is 0. And then the G is the gravitational acceleration in the downward direction. So you have to resolve the gravitational acceleration in the inclined plane. So G sin theta is the gravitational acceleration along the inclined plane, which is from here to here, okay. So G sin theta is your A, okay. So you can express V in terms of this one, okay. So this is the expression for your induced EMF. Write an expression for the induced current when there's a resistor of resistance R connected between the rails, okay. So you know that induced EMF equal to induced current times R, okay. So you can get the expression for the induced current. A metal conductor of length 20 cm is being moved with a constant velocity of 5 meters per second by a constant force F in a uniform magnetic field of 4 Tesla. Okay, so you know that the mechanical force is acting on the conducting rod. Okay, so that it can move at a certain velocity here. So the ends of the conducting thread, which has a negligible resistance, is connected to a resistor of 5 ohm. Find the magnitude of the force F. Okay, when you know that the moving conductor is moving at a constant velocity, you know that there is no acceleration experienced by the metal conductor. So the net resultant force on the moving conductor is 0. So you know that the magnitude of mechanical force is equal to the magnitude of the magnetic force on the conducting rod. And then you know that they are always at opposite direction. Okay, so when the conducting rod is moving from here to here, the magnetic flux linkage increases. Okay, so you want your direction of the induced magnetic field to be in out of the page direction. Okay, so this is the induced magnetic field, and then you want your induced magnetic field to be out of the page. Therefore, the direction of the induced current is in this direction. Okay, because it wants to produce an induced magnetic field which is out of the page. Or you can also consider the Fleming left-hand rule, okay, whereby you know that the motion of the free electrons must be downward. So you know that the current must be in upward direction. Okay, upward direction along the moving conductor. Okay, so mechanical force equal to magnetic force equal to BIL, I equal to E over R, and then back EMF is equal to BLV. Okay, so you can get the expression for the mechanical force, then you can find out the magnitude. A wire moving by an external force at a constant velocity V along a U-shaped conductor of width L is shown. A uniform magnetic field B is directed perpendicularly into the plane of the U-shaped conductor. If the resistance of the wire is R and the resistance of the U-shaped conductor is negligible, the external force applied on the wire is... Okay, this is the back EMF. This is the induced current. This is the force. Okay, because you know that the mechanical force is equal to the magnetic force when V is constant. This is what? This is the electrical power. Or you can also say that this is the mechanical power. Okay? Because when the wire is moving when the rod is moving at a constant velocity, you know that the electrical power is equal to the mechanical power. A metal rod of length L which is placed on two parallel conductors in a magnetic field which is directed perpendicularly into the plane is shown. The two parallel conductors are separated by the distance L and connected by a resistor R. If the metal rod slides at a constant velocity V, which expression represents the applied force? Okay, so you know that F equal to B squared L squared V over R, where you have already derived just now. Okay, so you know that the L is the length between the metal tracks, not the real length of the whole conducting rod here. Okay. A pair of smooth conducting rails in a uniform magnetic field is inclined at 20 degrees to the ground. Okay, so you know that the theta here is 20 degrees. A 1.2 meter long steel rod of mass 1 kilogram is allowed to slide down from rest on the rails. Assume that the field of flux density 0.53 Tesla is perpendicular to the ground. Please determine the magnitude of the induced EMF in the rod at an instant when its speed is 5 meters per second. Okay, so once again, you have to resolve the B to the direction perpendicular to the motion of the conducting rod. Okay, so B perpendicular to the motion is B cos theta, and therefore you can find out the back EMF. One end of both rails are joined with a wire of resistance 2.5 ohm, forming a closed circuit. If the rods and rails have negligible resistance, calculate the terminal velocity of the rod. When you see the word terminal velocity, then you know that the rod is achieving the maximum velocity already. That means that the velocity is a constant. Therefore, the acceleration of the rod is 0. So the net force on the rod is 0. So you know that the magnetic force in this direction is equal to the magnetic force on the conducting rod in this direction. Okay, so mg sine theta must be equal to F cos theta. Okay, so the magnetic force is this. And then cos theta, okay, because the angle between here and here is theta. Okay, so you can get the value of the terminal velocity. And then you notice that when you are getting the back EMF, you already have a term cos theta here. And then when you want to resolve your magnetic force in this direction, you use another cos theta. So at the end of the day, you have cos squared theta. Okay, this is quite important. Yeah? Okay, so if I ask you what is the transformation of the energy, then you will say that it is from gravitational potential energy to the heat dissipated by the resistance 2.5 ohm. Okay, because you know that now the rod is having the terminal velocity already, so you know that there is no increase in the kinetic energy of the rod. Okay. So in the next video, we will talk about the EMF induced by changing the angle between B and A, okay, which is a rotating coil. Thank you.